So today we are going to tell you about the RSA, Public Key Encryption. It is made out of 3 MIT students in the 1980s. So let's start. What is RSA Public Key Encryption? It is a branch of cryptography which involves multiplying a big prime number, which is easy, as you know, and factorizing very large numbers, which is apparently very hard.
So, for example, there's two people, Alice and Bob. Bob has a door, got two keyholes. Bob put the door open and puts a key in front of it. It is a key that can only lock the door. To Alice, who wants to send a message to Bob, puts a message in the house and locks the door with the locking key. This is the use of a public key. Bob knows he got a message looking at the door closed. He has either the other key, which is private, that can open the door. He opened the door with the key and get Alice's message. This is the use of a private key. So for another example which you can actually relate to, this is my email address, which is basically a public key. Now anybody can look up my email address, but they can't go into it because the password is like the private key. And yeah, I don't know that.
Yeah.
So when somebody sends me an email using the public key, only you can look at the mail, as it's the only one that have the matching private key. So, the use of maths in RSA encryption. Simply, it is an invertible function, as all codes are. If there is a function f to x which encodes the message, there will be an inverse function f
to the inverse of x.
F to the inverse of x, which will decode it in the RSA encryption. Anyone can encode using the function, and the variables which are the public keys. However, only the receiver can decode it, as he had the right variable that can make the inverse function to give a 1-to-1 matching x value.
So as Lloyd said, there is always a function that encodes a message and an inverse function which decodes a message. So this time we're going to look at the formulas of that function. So if we start p, let's say p is a prime number, a very big prime number, and q, another prime number which is very big. This will be useful because multiplying a prime number is very easy, as I said in the first part, but factorizing a big number, just a number, as a prime, two primes, will be really hard. And then to move on, M will be message, C will be the coded message. In numbers, we will be using the ASCII code of America. And E will be the relatively prime with phi of n, and phi of n here will be promised as p minus 1 times q minus 1. So E will be a prime number, relative prime with p minus 1 and q minus 1. First, the encoding formula is C is congruent to m to the power of e mod n. Mod is modular function, which you can see if you find out in the internet. Then decoding formula is m, which is the message, is c to the power of d to the mod n. So after I got the public key, n and e, I can now encrypt a message to give to Lloyd. So I chose how are you. So how are you in ASCII code is 72 something something something. However, if it goes over 100, it's hard to encrypt. So I just deduced 32 from each of them, and I'm going to add 32 after it, so to make it same. So if I did that, it gets 40, 79, 87, 0, 65, 82, 69, 0, 89, 79, 85, 31. And each of the blocks, as I said, refers to a letter. And 0 is a space bar and 31 a question mark. And using that formula again, and E and N, as N was 910,729, I use each block on that formula to get a crypted block. So for example, 40 in that formula will be 40 to the power of E, which was 881, mod 910,729 will be C. And C became 887 after encrypted. I used the computer because that number is really big, which cannot be expressed in a calculator when cryptography needs integers, not zeros. Same as the example 40, if you put every block, 79, 87, on the part of M of the formula, you can get a number like this. The reason I made it as 6 numbers in each block is that it is also to make it harder, or it is also to just make it easier to show. So after I did it all in the computer system, I got 8876826 055742 328 943 788 blah blah blah. So now Lloyd, after gets that big number message, has to decrypt it using the formula M, which is the message will be like as an ASCII code, is C to the power of D mod N. So obviously it just becomes how are you after adding 32 on the ASCII code. That's how the example works, and RSA public key encryption works. Simple. To sum up this video about RSA public key encryption, we're going to talk about the advantages, disadvantages, and some uses in the modern world. As an advantage, as I've shown you, it is very hard to decode or intercept. So, as you see, Bank of England, GCHQ, every internet system uses this kind of RSA encryption because it is really hard to break. However, there are some disadvantages which Lloyd will explain to you.
The disadvantages is that it's a bit complicated, and the impact would be massive if somebody develops an algorithm or a quantum computer that easily factor big numbers. All internet banks and secret sectors will have to develop new encryption methods. Usage of this cipher is for emails, banking, and secret codes. All done.
Thank you very much. Sorry for the bad.